Good morning. In the last class we had seen about determination of the parameters of a single phase transformer, determination of equivalent circuit parameters, right. So, we actually looked at two of the tests, one is open circuit test, the other one is short circuit test. These are the two tests we looked at, and in open circuit test we said we will get three readings, V naught, I naught and W naught, and short circuit test we said we will get again three readings, VSC, ISC and WSC. We also said that in open circuit test the reading that we get as W naught is corresponding to only the iron losses. There is no indication of any copper loss in this. That is because if you actually think about the equivalent circuit corresponding to open circuit test and short circuit test together, I am going to have the equivalent circuit somewhat like this for the single phase transformer. If I look at the open circuit test, I am going to have this on open circuit condition, which means the current that is flowing here, which I may call as I2 dash, this is equal to 0. And if I am looking at actually the current that is flowing here, which will be I1 during the open circuit condition, what actually flows during the open circuit condition here is only IC, which is actually corresponding to core loss component of current, and IM, which is corresponding to the magnetizing component of current. So, I1 will be equal to actually the summation of these two currents IC and IM, which is actually I naught. So, I am going to have essentially only I naught as the current that is flowing through the transformer under open circuit condition when I apply rated voltage V naught. So, V naught is rated voltage what I am applying. So, under this condition I am going to have, we already talked about this, that I naught will be only about 5% of whatever is my I rated. So, if I look at the drop that takes place in R1 and X1, it is going to be the drop across R1 and X1, drop across R1, that is R1 plus JX1 multiplied by I naught is going to be very low. It will not be much at all, because of which reason I am going to get actually this drop is really negligible. So, I can say drop across R1 plus JX1, that is multiplied by I naught during open circuit condition, this is negligible, and there is no current in the secondary side at all. So, I naught square R1 is negligible. So, we would say copper loss under open circuit condition can be neglected. Whereas, if I look at actually I naught square multiplied by R2 or R2 dash, no current flows through R2, right, because the secondary is open circuited. So, I am going to have no copper losses considered during open circuit condition. So, I can say that basically the W naught value what I get during open circuit is equal to iron losses themselves. Copper losses are not considered at all. Whereas, if I try to look at what is the value of the loss that I get during short circuit condition, the voltage that I apply during short circuit is going to be R equivalent plus J X equivalent multiplied by I rated. This is only about 1% or 2% of Z normally, or if I try to look at what is Z load. Similarly, this will be only about 3 to 5% of Z load. So, overall I am going to look at this, if I call this as VSC, that is the voltage drop during short circuit. This is going to be only about 5% or less than 5% of V rated. If this is going to be less than 5% of V rated, then I can say the voltage applied is equal to less than 5% of V rated, in which case, so if it is less than 5% of V rated, then I am going to have essentially V divided by F, that is what is flux. So, flux is going to be proportional to V by F, due to which I can write this is 0.05 times V rated divided by 50 hertz, due to which I am going to have actually flux under short circuit condition is less than 5% of rated flux. So, I am going to have essentially the iron losses which are proportional to flux square approximately will be very low during short circuit condition. So, the losses WSC value indicates only copper losses. So, we make basically the assumptions during open circuit condition or open circuit test condition is, first thing we are going to say is that the losses are only iron losses and copper losses in the primary are neglected. And of course, there is no secondary copper loss at all, because secondary is open circuited. Similarly, I can say assumptions during short circuit condition is actually, we are going to apply, we are going to look at only the losses as only copper losses, and that is actually PCU rated, that is rated copper losses. So, the second thing is the iron losses are neglected, right. So, these are the assumptions that we make during open circuit test and short circuit test. Now, let us look at efficiency of a transformer. So, the efficiency of a transformer is basically the output divided by the input. So, output, let me write this as V2 I2 cos phi 2, where cos phi 2 is actually the power factor of the load, divided by, again I am going to have output plus PCU plus P iron. So, the iron losses and copper losses need to be added, so that that makes up for the input, right. So, let me write this as V2 I2 cos phi 2 divided by V2 I2 cos phi 2 plus I should say I2 square R2, that is R1 plus R2, which I may call as R equivalent, plus I should say P iron. As long as I operate the transformer under a rated voltage and rated frequency, I will have basically the iron loss to be a constant. So, Pi will be constant. So, I can call this as either iron losses or constant losses, or I can say this is the hysteresis loss plus eddy current loss, right. This we already talked about. Now, let me write under what condition efficiency is maximum. Let me try to derive this. Under what condition, right. So, let me write the expression V2 I2 cos phi 2 divided by V2 I2 cos phi 2 plus I2 square R2 plus P iron. This is the efficiency. So, let me write under different load condition, right. I am going to have I2 to be different. So, let me differentiate the efficiency with respect to I2 and I make it as 0. So, in which case I am going to have actually, let me probably divide the numerator as well as divide the denominator by I2. So, I can write V2 cos phi 2 divided by V2 cos phi 2 plus I2 R2 plus Pi divided by I2. This is what is equal to, the efficiency. So, I can write, when I differentiate this, I will have to mainly differentiate only the denominator, nothing else. So, if I differentiate this, that is sufficient, because this looks like a constant. This is not going to matter. So, I can write basically, when I differentiate this, I would have I2 square R2, right, plus I am going to have Pi differentiated with respect to I2. So, I am going to have basically, this is I2 square R2 divided by Pi by I2 has to be differentiated. This has to be differentiated with respect to I2. So, when I differentiate this, I will have I2 square R2 equal to Pi. This is what I am going to get as the expression when I differentiate it and then equate it to 0. This is what I am going to get, which means when copper loss equal to iron loss, that indicates the maximum efficiency condition. This is the condition for maximum efficiency, right. Let me understand this situation clearly. P copper rated will be equal to I2 rated whole square multiplied by R equivalent. P copper at any other load, which is maybe X percentage of P rated, then I should write current will be equal to X times I rated. So, I can write PCU at any other load will be X I rated whole square into R equivalent, which will be actually X square into PCU rated. So, I can say if a transformer, if a transformer has PCU rated to be 200 watts and P iron to be 100 watts, efficiency will be maximum at that load where PCU at any other load equal to 100 watts. So, I can write this as X square times PCU rated is equal to P iron. So, this is X square times 200 equal to 100 watts. So, X will be equal to square root of 1 by 2. So, when the load is at 70% or 70.7% of the rated load, then efficiency is maximum for this particular transformer. So, if I try to plot actually efficiency versus load condition. So, let us say this is 100%, this is 50%, so 70 lies somewhere here. So, I am going to have probably the efficiency will start with 0 and it will reach maximum around this condition and then it will start falling again. So, this is what is the maximum efficiency. So, this is what we mean by saying what is the maximum efficiency condition of a transformer. So, we told already that there are mainly two major performance parameters for a transformer. One is efficiency, which we talked about already. The second one is going to be regulation. So, regulation actually talks about how well the output voltage is maintained as a constant irrespective of the load power. So, this is what, and power factor of course, this is what we mean by voltage regulation. What we mean is, if I apply, let us say it is a 200 by 100 volts transformer, if I apply 200 volts irrespective of the load whether the output voltage will be at 100 volts or not. This is what we mean by talking about efficiency, regulation. So, when we actually look at the transformer equivalent circuit, we have R equivalent, we have X equivalent, we apply V1 here and what we are getting here is V2 dash or VL dash. We are neglecting the parallel components. We do have some parallel component somewhat like this, but we are planning to really neglect it because these are going to carry very small current. The current is really small, current is less than 5% of I rated. So, I can afford to neglect it. So, I can say the drop, that is V1 minus V2 dash, is going to be basically R equivalent plus J X equivalent multiplied by I load. This is what is going to be. So, I load is actually flowing here, this is I load. So, I can afford to neglect the parallel component of current. So, I can say I load multiplied by R equivalent plus J X equivalent is going to be the voltage drop. So, voltage drop is equal to R equivalent plus Jx equivalent multiplied by I load, and I have to look at I load also along with its power factor, otherwise it does not make sense. So, now if I may call this as V drop, I can say regulation in percentage, if I try to look at, will be V drop divided by rated voltage multiplied by 100. This is what is percentage regulation. So, if I actually draw the phasor diagram, I should say this is what is my voltage, which is actually V2 dash or load voltage. Now, I would say maybe my current is lagging behind by some angle. Let me call this as I2 dash or I load. Maybe this is at an angle of phi L. This is the load power factor angle. Now, if I try to look at what is I2 dash multiplied by R equivalent, it will be in parallel with this. So, this is I2 dash multiplied by R equivalent. Perpendicular to that will be I2 dash multiplied by X equivalent, and what I look at here as the summation of these two, this will be I2 dash Z equivalent. If I actually extend this, please note that this angle, if I extend this here, this angle is same as phi L, whereas this entire angle I am going to call as the inherent impedance angle of the transformer, which is phi equivalent. Now, when I add this I2 dash Z equivalent to that of V2, I will get the overall voltage, which is actually V1. Of course, I have drawn the whole thing in the exaggerated fashion. Now, I can say V1 minus V2 dash will be equal to I2 dash Z equivalent. So, this is what is the voltage drop. I can write rather this as the summation of, let me call this point as O, this point as P, this point as Q, this point as R. So, I can say that OR square will be equal to OP plus OQ the whole square plus PQ square, right. And OP is, after all, if I write what is OP, OP is equal to V2 dash, OR is equal to V1. So, if I neglect this RQ square, not PQ, I am sorry, RQ square. So, if we neglect RQ, then I can write this as OR minus OP equal to OQ. So, OQ becomes my regulation. If this angle is small, then I can afford to neglect this vertical component of this voltage drop. So, this angle, if I try to write what this angle is, this angle will be phi equivalent minus phi L. So, sine of phi equivalent minus phi L, this we are neglecting, this is neglected. So, I can write now V1 equal to V2 plus, let me go back to the previous one, that is actually OQ. So, I am writing basically what is OQ. So, OQ. So, let me write what is OQ. OQ, if you look at, OQ is basically whatever is I2 dash ZQ cosine component of that, I2 dash ZQ cosine of whatever is this angle. So, that will give me, this is I2 dash ZQ cosine of phi equivalent minus phi 2 dash. This is what is going to be my, or rather phi L or whatever, this is what is going to be my OQ. So, I would say voltage drop is equal to OQ, which is equal to I2 dash Z equivalent cos phi equivalent minus phi L. So, in which case I can write this to be I2 dash Z equivalent. You guys know better the expansion of cos phi equivalent minus cos phi L. So, I can write cos phi equivalent cos phi L plus Z equivalent sin phi equivalent sin phi L, right. Cos of A minus B equal to cos of A plus B, cos A cos B plus sin A sin B. So, we are essentially going to write this Z equivalent times cos phi equivalent. We wrote it already in short circuit test also. That will be essentially R equivalent cos phi L plus X equivalent sin phi L. So, this is the voltage drop. So, percentage regulation at any load current I2 dash will be I2 dash multiplied by R equivalent cos phi L plus X equivalent sin phi L divided by V rated, the whole thing multiplied by 100. This is what is regulation. This is an approximate value of regulation. Now, with this we should be able to say if the power factor is lagging, cos phi L is positive, whereas sin phi L is going to be negative, right. And please remember, this expression was derived assuming a lagging power factor. That is why we got cos phi equivalent minus phi L. So, we should be able to write voltage drop will be equal to I load or I2 multiplied by R equivalent cos phi L plus X equivalent sin phi L, whereas if the power factor is leading, I am going to have sin phi L will have an opposite sign, that is, I am going to have this to be positive. So, V drop will be I2 times R equivalent cos phi L minus X equivalent sin phi L. So, whenever we have a leading power factor, it can so happen that R equivalent cos phi L and X equivalent sin phi L can cancel out with each other and we may not get any drop at all. By chance, if X equivalent sin phi L is dominating over R equivalent cos phi L, then we may get a positive regulation. So, for lagging power factor, voltage at the secondary terminal will fall, whereas for leading power factor, voltage at the secondary terminal will not fall as much as for lagging loads. In fact, the voltage can rise. It need not even fall, it can rise. So, whenever we have capacitive load, we will see that the secondary voltage rises. So, this completes our discussion on what we had seen so far is equivalent circuit parameters, right. We had seen OC and SC test, we had seen regulation, we had seen efficiency. Now, a few more topics that are pending that we need to address are auto transformer or a variac, how we are going to really connect. This will be a single winding transformer. We will be looking at this. Then we will also be looking at current transformer and potential transformer. Which we would use basically for measuring voltages and currents. So, generally they are used in instrumentation. So, sometimes they are also known as instrument transformers. After finishing with these things, we will also look at three-phase transformers. Then last but not the least, we will look at parallel operation of transformers. So, this may take like 3 to 4 lectures. So, we will be discussing those as well after this. Okay. So, these 4 topics we will take up after finishing up these, having finished equivalent circuit parameters, open circuit, short circuit test, regulation and efficiency. We would be taking up these things. We would work out some more problems on OC/SC test, regulation and efficiency, which would make actually the understanding much clearer than what you have understood already. Okay? So far so good.